Okay, today we're going to talk about some more units associated with fluid power and how they're going to shape our view of fluid power. A lot of these are going to be very important later on. Again, everything builds off of one another, so it's important that we understand the units and what they mean. And then we will be using those in formulas moving forward. So the first thing we need to look at is density. Of course, density is mass divided by volume. Of course, we know what mass is. We should know what mass is. It's the amount of material in something. Of course, we know what volume is. Volume being how much space that material takes up. And density is basically how much mass per unit of space. Okay, something that has a higher density tends to be heavier because density is or mass is directly related to force when placed in the acceleration of gravity or acceleration due to gravity. So how are we going to use density with materials? Well, in fluids, different fluids have different densities. Something like oil is less dense than water. Now, what happens if something is less dense? It tends to float, right? That's the reason why we have something that's less dense is going to float. Something more dense is going to sink. Something that's the same density is sort of just going to float there. It may go up and down. And again, something even with a little less density is still going to float. So oils we know float on water, and it's because they're typically less dense. We're definitely going to be looking at this and how it relates to specific weight in just a second. So force is using Newton's laws, mass times acceleration. Cool little thing I use to remember it if you're a Star Wars fan is if I erase, may the mass times acceleration be with you. Alright? And I should probably change my pointer color here. Yeah, but may the force be with you, right? Mass times acceleration. There's your cheesy joke for the day, right? So what does that mean? Well, if our mass increases, right? Acceleration stays the same, so this is the same, then our force is going to increase. And that's the principle of weight. So weight is just a force, right? This is weight and is in pounds force. So it is a force that's directly proportional to mass because acceleration, at least on Earth, is the same at 9.8 meters per second or 32.2 feet per second squared. All right, that's gravity. So we will look at force. The main thing that we really reason why we look at force in this particular way is because of the units. So force is mass times acceleration. So F equals ma. So if we look at the units of force, something like a pound force equals mass. Well, mass is in slugs times acceleration, which is in feet per second squared. Of course, this is understood to be over 1. So what is the units of force? It's actually a slug foot per second squared. That equals a pound force. This may seem kind of weird right now that that's the case, but it is the case. So what is the units for something like a Newton? Well, instead of slugs, we're going to use kilograms. Understood to be over 1, right? And this is going to, instead of be feet per second squared, it's actually going to be meters per second squared. So that's going to give us a kilogram meter per second squared equals a Newton. So again, we're just doing this because these units are going to be important later on when we need to get back and forth. We may end up needing to convert a pound force into a slug foot per second squared, or a Newton into kilogram meter per second squared. Alright, specific weight. So we have force divided by volume. Okay. So I will let you know that is not the base unit. We can actually break this down. Well, actually, let's get past that for right now. But anyway, the specific weight, force divided by volume. You can again, I could substitute in here pound and Newton. What we just talked about, kilogram meter per second squared. We could get something completely different, but for right now, this is best to keep things simple. We'll leave it as Newton and pound per some volume squared, so Newton per meters cubed and pound per foot cubed. So specific weight and density have one thing are only separated by gravity. So if we want to go from specific weight to density, we only have to worry about we can factor the gravity in and out and get a conversion between the two, and we will do that. One of our problems. But a lot of times, the better thing to do is just to go to specific gravity. And specific gravity is pretty awesome because it's unitless. So we don't have to worry about if it's SI units or if it's whatever. It could be, you could have a specific gravity of a fluid, and then you can take that and go to kilograms per liters. You could go to newtons per liters. You could go to whatever you'd like because it's unitless. So, but it describes the density or the specific weight of a fluid as it compares to the density of water. So, to find specific gravity, you can take the density of the fluid divided by the density of H2O. You can take the specific weight of the fluid divided by the specific weight of the H2O. Now, the main thing here to remember is that because this is unitless, right? This is unitless. Then this unit and this units must match. If they don't match, then this is no longer unitless, right? So they have to match. So when you divide one unit by another unit that's the same, then you end up with something that's unitless. Same thing for the specific weight. So anyway, we've got specific gravity is a lot of times how fluid is described. So you'll look at fluid, it'll tell you the specific gravity, and then you could find out its density in any unit you would like, or its specific gravity in any unit, or a specific weight in any unit you like, as long as you know the units of that you like of H2O. So let me make sure. I don't know if I've added this in here. Let me go to the next slide just to check. No, I have not. So let me go ahead and put on here the specific weight of H2O, and this is in your unit packet. You have 2, which is 62.4 pounds force per feet cubed, and you also have 9,807 newtons per meter cubed, and then you have density, and of H2O. And that is going to be 1.938 slug per foot cubed and 1,000 kilogram per meter cubed. Okay, that's in your that's going to be in your unit packet as well, or your formula packet. All right, head pressure. Head pressure is the pressure generated by a fluid that has some depth. Okay. So the only thing that determines the head pressure, so pressure like for example right here, and so you can't hardly see it because it's in white, but options. So right here, this is pressure, is going to be two things. It's going to be the fluid height. Okay, so here's our height. And the fluid specific gravity. More specifically, which is right here. More specifically though, the specific weight. Okay, so that's going to be in this formula in here. So pressure equals fluid specific weight times fluid height. So how does that work out? Well, let's say we have our specific weight in something like pounds force per foot cubed. Okay, we times it by some height in feet. Okay, we're going to knock off the cube and it's going to go to squared. So our final units are going to be pound force per feet squared, which we know is a pressure. So the fluid height is the only thing that determines pressure. Now, this is a common misconception. Something like this, something like this, and something like this all have the same pressure. So I usually will make a couple of graphs and say, okay, we got a water tower here, right? And then we have another water tower. They both have the same fluid height, okay? So we measure the pressure at both ends. Which one has the higher pressure? And usually people say this one, but that's not correct. They both are equal to each other, okay? Only thing that makes a difference is going to be the height of the fluid and the specific weight of the fluid. Of course, specific weight is always directly proportional to specific gravity. So if you know specific gravity, you can find specific weight. Alright, so we have a long example. So hopefully you will bear with me while we go through it. Let's start over here. So we have lead has a density of 11.34 grams per centimeter cubed. So first thing we want to do is go to slugs. I want to do this one first. Let me go ahead and go back to white. So we're first going to do it in slug per foot cubed. So we're going to do that up here. 11.34 gram per centimeter cubed. We're going to go 1 kilogram equals 1,000 grams. We have 1 million centimeters cubed is 1 meter cubed. slug equals 14.59 kilograms. This is all from your formula packet, by the way. 1 meter cubed equals 35.28 feet cubed, which is just 3.28 times 3.28 times 3.28. There's 3.28 feet per meter. So, and we end up with 22.03 slug per feet cubed. Now from here, the easiest way to get specific weight in these two units and density in this unit is actually to go to specific gravity. But we're not going to do that. We're going to go the long way around to get to kilograms per meter cubed. That's actually much simpler. We can just do 11.34 grams per 1 centimeter cubed. And then, of course, we've got the above calculations, 1 meter cubed and 1 kilogram, 1,000 grams. And grams cancel. Meter cubed cancel. So we end up with 11,340 kilograms per meter cubed. So there's this one. So let's go ahead and check mark that one. So there's that one, there's that one. There's one answer. There's two answers. So the weight of a 1 foot cubed block of lead, okay? So this one's pretty interesting. We can do it with 22.03 slug. Give me a break, come on. Alright, slugs per feet cubed. Okay, and then we can do 32.2 feet per second squared. So we have a final unit here of 709, and it's going to be slug. I'm not going to cancel out the feet for right now. Times feet per second squared times feet cubed. Now, if we look at just this part of it, we'll notice that a slug foot per second squared is actually just a pound force. So we actually can rewrite this as 709 pound force per feet cubed. Okay, so this is our final answer. And that is the reason why we have to talk about force, because the unit here comes into play. And again, this is a conversion in between specific weight, or I'm sorry, density to specific weight. So we've got our specific weight here, and then specific weight in Newton per meter cubed. Again, we can do the same thing. In this case, we're going to do 11,340 kilograms per meter cubed. Okay, and we're going to multiply by our 9.8, which is just gravity, by the way, meter per second squared. And we're going to end up with 111,132. The unit will be kilograms meter per second squared times meter cubed. And if we look at just that part, we'll know that that's a Newton. So it's actually, our final answer is Newton per meter cubed. So there's that one. I'm sorry. There's that one. So the weight of 1 foot cubed of lead, that's pretty easy. The weight is just going to be the 709, and then the weight of 1 meter cubed of lead is actually going to be 111,132 newtons. So those two are actually done as well. We can check mark off those. The last one's really just specific gravity, and because weight was such an easy one. And that's pretty simple. We can take anything we want to. We could take this one, we could take that one, we could take that one. All of these different units could actually come up with the same answer. The one I'm going to do is, we'll do, actually let's just create a new slide here. See what, let's just do it with one of them. So we can find specific gravity equals specific weight of the fluid divided by the specific weight of H2O. So that would be something like specific weight of the fluid being 111,132 newtons per meter cubed divided by 9,807 newtons per meter cubed, and that's going to give us 11.33. We could also do equals the 709. That would be in pound force per feet cubed divided by 62.4 pound force per feet cubed, and that's going to give us the same answer here, equals 11.33. So you can do it any way you want to. You could do it with the density. You can do it with slugs. Of course, there is 1.938 slug per feet cubed in the density of water. We could do it with density in SI units, which there's 1,000 kilograms per meter cubed for the density of water in SI. And then we just did it with specific weight in SI and specific weight of British gravitational. So there's that one. They all come up with the same answer. Hopefully that's not too confusing. Last example, or second example. Find the pressure at the bottom of a water tower, and if the water tower is 200 feet of water height converted to pounds per square inch. So let me draw a water tower here, and let's say that it has 200 feet of height. So we know that pressure is going to be equal to specific weight times height. So pressure equals specific weight of water is 62.4 pounds. Should I see pound? pound force per feet cubed. And then we're going to times this by the some height, which is going to be 200 feet. Feet's going to knock off one of the feet over here. We're going to end up with 12,480 pound force per feet squared. Then of course the simple conversion, 1 foot squared is equal to 144 inches squared. And that's going to give us 86.6 repeating pounds per inches squared, or 86.6 repeating psi. Alright, that is it. That's head pressure. Again, looking at the units, watching the units is going to help you a lot, making sure you get the right answer. If you have any questions, let me know.